So now it's the second half of the afternoon session, and the speaker is Professor Carroll from Hopkins University again, who is a professor of natural philosophy, right?
That's right.
Which is referring to the website, which sometimes also deceives us. And as it's written here, the talk by Xiang today is entitled The Quantum Past Hypothesis. No, sorry, the arrow of time in unitary quantum mechanics, because time sometimes is digressive. I was diverted to the previous talk. So the title, I repeat myself again, is The Arrow of Time in Unitary Quantum Mechanics. And now the floor is yours.
All right. Thank you very much. Yeah, it's great to be here at this meeting. It's good to be in meetings where I don't need to convince people that, philosophy and physics can talk to each other and have interesting things to say. You're already convinced of that. I will have to convince you of other things, I suspect. But this is the title. It begins very much as something that's going to build on Sakshi's talk. So if Sakshi hadn't been here, I would have had to talk a lot faster to convince you of a lot of things before I get to what I wanted to say. So the context here is that for a while now, I've been working on this idea that you really should take quantum mechanics totally seriously and literally at the same time, by which we mean you shouldn't start with a classical theory and quantize it. You're allowed to do that, but that might not work. And indeed, the fact that we haven't been able to quantize gravity is maybe a little bit of evidence that it doesn't always work. What we should always be able to do is start with a quantum theory and find a classical limit. So what do you mean by starting with a quantum theory? Because usually we start with like space and then we make a wave function or whatever. Well, you have Hilbert space. I call it unitary quantum mechanics just to not get people all excited, but it's really Everett in the most extreme form, where we don't have any classical baggage that we're bringing along. So sometimes called Hilbert space fundamentalism or Mad Dog Everettianism. We take the most austere, beautiful, minimal version of quantum mechanics and ask how the non-logically acceptable world can emerge from that. And what are the ingredients? We have Hilbert space, we have some initial state, or maybe a density matrix. We're not going to get into that argument today. You have a Hamiltonian that drives Schrödinger evolution, in the case where it's a pure state. What does it mean to say you have a Hamiltonian? If you help yourself to classical baggage, like space and fields and things like that, you might express the Hamiltonian as a sum of operators. We don't have that. We're not allowed to do that. All you have, the only basis in Hilbert space that is picked out by the Hamiltonian is the energy eigenbasis. So you have the Hamiltonian in the energy eigenbasis, where it's a big diagonal matrix, and its eigenvalues, the diagonal elements, are the spectrum of the Hamiltonian. So you have literally a list of real numbers, and you're asked, okay, what is that? Sometimes you could answer that question. If you're really good, you can say, oh yes, that's a qubit, or that's a simple harmonic oscillator. I want you to be able to say, oh, that's the standard model of particle physics plus gravity in 3+1 dimensions. That's ultimately what we want to be able to do. We're not there yet. So we're going to try to see whether or not all that stuff can emerge. And I'm actually not defending this program here today, so you're not allowed to doubt it. I'm going to try to explore some of the ramifications of the program. I will give you 2 slides on how it might possibly work, that you could derive all of the world from just the list of energy eigenvalues of the Hamiltonian. The basic strategy is quantum mereology, that is to say, dividing up Hilbert space into subspaces, or at least subsets in some generalized form, that give you some kind of structure you can hold on to, like an idea of locality, an idea of interactions. As Guy's talk emphasized to us, he should have come after mine, because he was doing a more sophisticated version where he said, maybe it's not so simple. That's fine. I'm going to be very simplistic today and just take the most basic view and then hope we can fix it up later. So the most basic view is, what do you mean finding structure? You mean finding a tensor product factorization of Hilbert space, for example, into a system, an observer, and an environment. And then when you say, well, the system looks like a simple harmonic oscillator. A simple harmonic oscillator is not just a list of energy eigenvalues with equal spacings. It's also the fact that you as the observer look at it and go, oh yeah, look, it's oscillating back and forth. That's super relevant to why you call it that. So the question is, what is the right way of factorizing Hilbert space? There's a big, big number, related by a big unitary transformation of different ways to factorize Hilbert space. So you invent some criteria for things you want to happen. And those criteria basically, they end up being some version of, you get a higher level emergent description, perhaps a classical description, perhaps a description that has the nice properties like locality, etc., that we're so familiar with. So as soon as you factorize Hilbert space, you already have a Hamiltonian just in terms of its spectrum, but now you have a decomposition of the Hamiltonian. And then you can say, oh, system A has its Hamiltonian, system B has its, and there's an interaction between them. And you can say, is the set of all interactions local? Does it have a classical limit? Do big, heavy things remain localized? All of those questions can be addressed. And whether or not you can do it is a good open question. So just as a little hint that maybe you can do it, there was this wonderful paper by Collier, Pennington, and Bernard, and they said, look, if I have a lattice with little qubits or something on it, and I have a Hamiltonian, okay? So I could assign my quantum mechanics students, diagonalize the Hamiltonian, find all of its energy eigenvalues. We're asking the question, can you go backward? So in quantum field theory, we know that, again, modulo weird things with gauge invariance and things like that, you can divide up space into regions and imagine all of the modes of the fields in those regions. And the whole Hilbert space is just a tensor product of all of them. But it's a very, very special decomposition because you have locality. Locality means that the modes in this region only interact directly with their nearest neighbors. There's no direct interaction between that factor of Hilbert space and that one. So that turns out to be a super strong restriction on what kinds of spectra of Hamiltonians you can get. Collier, Pennington, and Bernard say that most Hamiltonians have no local factorization, and when it exists, it's mostly unique. Again, there's a bunch of footnotes that are very worth talking about, but it's an encouraging result to say that maybe the simple list of energy eigenvalues has enough structure in it that you could recover the world if you thought about it carefully enough. And then my collaborators and I pointed out that if you go beyond just the division into factors and look at entanglement between the factors in states that are close to the ground state, you can use the amount of entanglement to define an emergent metric. And in the weak field limit, with some assumptions, which we make and list, you can actually derive Einstein's equation for that emergent metric. Now that's not as impressive as it sounds. There's not that many other equations you could derive. But the point is, it points toward how you can get a dynamical space-time geometry in this framework in a very natural way. Okay, that was all the justification for the program. Now today we're going to focus on the arrow of time and try to match it to our observable universe. So this is a picture of the observable universe, if you remember. Many cosmologists will show you this picture, but only show you this part, going up to today. There is a future to the universe, and we're assuming, for simplicity, that the acceleration of the universe, which is empirically measured, is due to a true cosmological constant. It's not dark energy, it's not modified gravity or anything like that, nothing dynamical, it's just lambda, like Einstein put it there. And so then the picture we have is, we don't know what happens at the very early time, but then there is expansion and cooling and recombination in the microwave background, and you make galaxies and structure. The galaxies, etc., will all fall into black holes, and the last black hole will evaporate a googol years from now. And then you have de Sitter spacetime. De Sitter spacetime is just a solution to Einstein's equation with nothing but a positive cosmological constant. There's a whole other wonderful talk to be given about the fact that entropy increases from here to there. These are rough estimates for the entropy in a co-moving volume of space. But you notice that the complexity of the universe starts very low, this is very simple, and it ends very low, this is also very simple, and it peaks in the middle. So entropy does this, but complexity does that. That's another fascinating talk that I'm not going to give. How would you fit this picture of unitary quantum mechanics into the expanding universe? We have no idea about a lot of this. Again, this is very sketchy, informal, preliminary program. But even beginning to think about it makes you go, oh yes, actually I'm getting some insight by thinking about things this way. There's a sort of semi-famous but usually ignored issue in cosmology with quantum mechanics on top, so not quantum cosmology, but just ordinary cosmology taking quantum mechanics seriously, what happens to Hilbert space as the universe expands? Right? I mean, as the universe expands, a volume gets bigger. I could, if I imagine there's some ultraviolet cutoff, now I can fit more things into the universe because it's bigger. That sounds like Hilbert space is getting bigger. But that can't be right. We don't have sensible versions of quantum mechanics where Hilbert space is getting bigger. So this approach offers a very natural answer to that question. Hilbert space is not getting bigger. It always was just as big. But most of the qubits in Hilbert space used to be unentangled. And what happens when space expands is really just there's a Hamiltonian, or if you like, a set of gates, if you're a quantum information person, that entangle more and more qubits that then join the subspace of Hilbert space that is forming the geometry of space. So there's a whole bunch of Hilbert space that is just not participating in geometry, and cosmological evolution entangles them, and we interpret that as the expansion of space. So you can draw a little quantum circuit for the expansion of the universe, and you can actually derive consequences from that as well. Okay. We're going to take a lot of, I'm just laying out a lot of preliminary stuff before we get to the action here. We're going to take a lot of inspiration from what is known about de Sitter space. So de Sitter spacetime is one of the maximally symmetric solutions to Einstein's equation, in this case with a positive vacuum energy. So we have a vacuum energy characterized here by the cosmological constant lambda. And that means that in a certain slicing of space-time, you have a constant Hubble constant, a constant expansion rate. And that means that we have a horizon. So here you are, here's a friend of yours who is very, very far away, 20 billion light years away. And the space in between you and them is expanding sufficiently fast that you're outside each other's future light cones. You can never come back and talk to each other ever again. And the point at which that happens is called the horizon. Obviously, there's a different horizon for every observer. It's not like a black hole horizon, which is a feature uniquely of space-time. It's an observer relative notion. But otherwise, it has a lot of the similar mathematical properties to a black hole horizon. Hawking did all the black hole stuff in the mid-70s, and then he and Gary Gibbons in 1977 did the same thing for de Sitter and showed that it has a temperature, it has an entropy, and if you think that de Sitter is the maximum entropy state for this set of degrees of freedom, which I think there's a good argument that it is. If you know the entropy of a maximum entropy state, you know the dimension of its Hilbert space, if you're interpreting that entropy as the von Neumann entropy. And the answer is the dimensionality of Hilbert space is e to the entropy. So that's a very big number, 10 to the 10 to the 122. It's not infinity. Those differences will matter for cosmology. But this is the Hilbert space for our observable patch of the universe, okay? What about the rest of the universe is a question for another slide. This slide, good. I don't have my PowerPoint, so I can't see what the next slide is coming up, so you have to let me guess. This is a picture that is actually meant to illustrate something called the cosmic no-hair theorem. Just like black holes have a no-hair theorem, that we make a black hole out of lumpy stuff, all the lumpiness radiates away and it settles down. Likewise, for a cosmology with a positive cosmological constant, the universe settles down. All the excitations, all the galaxies and perturbations go outside our horizon, and you really do approach a pure de Sitter spacetime. This whole square is the conformal or Penrose diagram for de Sitter. So the question, what is the dimensionality of the Hilbert space of the universe, of all of reality, of the theory of everything? In a universe with a positive cosmological constant, we're not imagining different cosmological constants in a landscape or anything like that. That would complicate it, and that's fine, but we don't need that today. There's still an important dichotomy between infinity and finite. The standard view would be, look, space expands forever and ever. This is a Penrose diagram, but these, this is the north pole of a sphere, this is the south pole of a sphere, this is the horizon, which is a null surface, and it's a weird conformal diagram, so the distance from here to here, the physical distance, is the same along every horizontal slice. So the total volume of space gets arbitrarily big in the future, And if you thought that every volume of space had some degrees of freedom, it would grow forever without bound, and Hilbert space would be effectively infinite. There is a view pushed forward by Tom Banks and Willy Fischler that says you're making a mistake because you're thinking too classically. In fact, every observer sees what's in their horizon, and they claim that black hole complementarity implies that other observers see their own horizon, but those are not independent of what you see. There's actually just a big unitary transformation that you can use to reconstruct the horizon volume of any other observer from yours. In other words, they're saying there is no such thing as outside your horizon. They're saying the whole universe is you and your horizon. And then the dimensionality of Hilbert space is a finite number. I don't know which one of these is true, so we're going to investigate both possibilities. And the nice thing is that when you take this austere picture of quantum mechanics, that quantum mechanics is the simplest theory ever. It's the best. I know that you probably took a quantum mechanics class and you thought it was hard. And that's because you had to solve all these equations and you weren't working in the energy eigenbasis. The Schrödinger equation is linear. It can't be a simpler possible equation. As long as you work in the energy eigenbasis, solving the Schrödinger equation exactly is trivial. You have energy eigenstates. These are the energy eigenstates. They don't change their direction in Hilbert space. They just rotate their phases. And I can write any state as a superposition of energy eigenstates. So I can work in the energy basis. And then if I know the energy, En, for the state n, I exactly solve this equation. The amplitudes here, the component length, just remain constant. And the phases rotate at different velocities depending on the energies. So any one state in a closed system, all of the evolution happens in what is called the torus of phases. The actual lengths of the different components don't change. All that changes is these phases, and they're periodic. So the set of all the evolutions is a big torus. One dimension of the torus for every dimension of Hilbert space. Okay, so we have solved the Schrödinger equation. That's good. Therefore, we are left with three options for what could happen cosmologically. So really, I haven't sneaked in many assumptions yet. It's that the universe is always obeying the Schrödinger equation, and that, I think that's it. I think that's what I'm assuming. There's an implicit feature of the Schrödinger equation, which is that time does not begin or end. So you see where you would get into trouble by taking classical gravity too seriously, where you have singularities and the Big Bang and black holes and all this mess. If you really think that the universe is described by a state in Hilbert space, it evolves forever. That's a theory. There's no beginning or end. So the only three options are, if the dimensionality of Hilbert space is infinite, then the evolution is eternal and non-repeating. The wave function sort of moves in Hilbert space forever and ever and ever, and it never comes back to where it started. If the dimensionality of Hilbert space is finite, and the spectrum of the Hamiltonian is generic, by which I mean I didn't finely tune the energy eigenvalues, then there is a recurrence theorem. Okay, this is equivalent to Poincaré saying in the solar system, the planets will eventually line up again, if you wait long enough. The phases of our energy eigenstates will eventually line up again, if you wait long enough. And you can even figure out how long it will take. It will take a very long time. E to the dimensionality of Hilbert space. Remember, the dimensionality of Hilbert space might plausibly be 10 to the 10 to the 122. So this is e to that. It's a very big number. But there's another possibility, which I've never really taken seriously, which is the focus of what I'm going to be talking about. What if the energy spectrum is not generic? What if it is finely tuned? And in particular, what if the ratio of any two energy eigenvalues is a rational number? That is to say, what if all the energy eigenvalues take the form some integer times some fiducial energy? It's possible. It's highly non-generic, but I can consider that. And what happens then is that rather than filling the whole torus, because the evolution is ergodic, I come back to exactly where I started, in a much shorter time, roughly the logarithm of this time. Still long, but much shorter than the recurrence time. And I'll show you the implications of that in a second. So what we're going to try to do in this framework is think about the arrow of time. And Sakshi already set us up. So we have this idea of, well, this is the classical picture where you have S equals K log W, as in Boltzmann's tombstone. You start in a low entropy state, and entropy naturally goes up because there are more high entropy states than low entropy ones. This is the quantum version where you have a set of macro states in a direct sum structure in Hilbert space. So that if you're in a single macro state, the Boltzmann entropy is just a logarithm of the dimensionality of that macro state, which is equivalent to W, the phase space volume in Boltzmann's way of doing it. And then if you're in a superposition, you just have the superposition of all those entropies weighted by the probability of being in that macro state. So that's the stuff that Sakshi already told you. Let's apply this to the cases of an infinite dimensional Hilbert space and a finite one. The big worry that we will have to keep in the back of our minds is the Boltzmann brane problem. Boltzmann, by the way, never knew about the Boltzmann brane problem. He was challenged in the 1890s by Zermelo to reconcile the fact that Poincaré had a theorem, recurrence theorem, you always just come back to where you started, with Boltzmann's claim that entropy just increases in a mechanical system made of atoms. You can't, Zermelo is a mathematician at heart, he never was really a physicist, so he says you can't have a function that is both periodic and monotonic at the same time. I know this because I'm a mathematician. And Boltzmann said, he wrote a paper saying, you dummy, you idiot, it's clearly wrong, and I'll give you 3 different reasons why it's wrong, and his 3 reasons are absolutely incompatible with each other, and he never tells us which one he believes in. One of them is maybe you just wait long enough. Maybe it's all true. Maybe the universe is finite. Maybe you do recur over and over again. Maybe you spend most of your time in thermal equilibrium. But if you wait long enough, there will be a random fluctuation that makes our galaxy, and then it dissolves backward, and maybe we live in the aftermath of such a fluctuation. So he invents the multiverse and the anthropic principle. And no one gives him credit for this, but he does deserve it. The problem is that the scenario hilariously doesn't work. And this is pointed out by Arthur Eddington, who said, look, you're Boltzmann, you should know this. There's the probability that you get different fluctuations downward in entropy, and it's exponentially harder to get a big fluctuation than a small one. So you tell me what kind of fluctuation you need to make an observer. That fluctuation might be exactly this room, right? Like, it might not be just you. You might say, like, I know this room exists, I'm going to insist this room exists. Eddington says, good. This scenario predicts this room will fluctuate into existence an infinite number of times, and almost always, outside, it will be thermal equilibrium. No, that's not a good way to go through life. That's just bad for all sorts of reasons. The minimal fluctuation is a Boltzmann brane, not this room, but a single brain-like thing out there in the void that just exists long enough to go, thermal equilibrium, and then it dies, okay? But the overwhelming numerical majority of observers are these random fluctuations, not thermodynamically sensible people like we want us to be. And the problem with this is that it's cognitively unstable. If you and all of your impressions about physics and mathematics and logic and philosophy just randomly fluctuated into existence, you have no right to trust them. And again, that's no way to go through life. Okay, can we avoid this problem? Well, yes, we can, but you have to be careful about it. So there's, again, 2 possibilities. Dimensionality of Hilbert space is infinite or finite. If it's infinite, you actually very naturally get an arrow of time. You very naturally get the idea that at almost every point in the history of the universe, entropy was much, much lower in one direction of time and much, much higher in the other direction. And you can think about this in toy models where you just have like a free particle and you invent some macro states for the free particle and then you can plot it, or you can ask your favorite LLM to plot it for you. This is the quantum Boltzmann entropy that Sakshi told you about for a free particle starting with some wave packet, okay? So in this case, I started with a very, very low entropy state, but it doesn't matter. If you start with any state, any normalizable wave function, and let it evolve, eventually in the far past and the far future, its entropy will go up. And you can even, in this simple example, show that it's logarithmic or something like that. The real question is not, can you get narrowed time, but can it look like our universe? And here, we have a favorite idea. This is called baby universe creation. You imagine that in empty space, there's a quantum fluctuation, makes a little bubble of false vacuum, which then pinches off and makes a baby universe. Does this happen in real quantum gravity? We don't know. Full employment for young graduate students to figure this out, to actually know. The consensus in the community has gone back and forth about whether or not this actually happens. But it leads to this beautiful scenario where you have now time is going vertically, and maybe you have just empty de Sitter space for most of the universe, but occasionally there'll be a little bubble of baby universe that pinches off, and that starts small, and it expands and cools, and you get an arrow of time. And you can play that game both forward and backward in time. So you get exactly the qualitative features that you had of the entropy curve here. It increases without bound both to the past and the future. And there's good parts and bad parts to this. I'm running out of time, so I won't dwell on it. This is still my favorite, 20 years later, after I first proposed this is still my favorite way of saying the arrow time could be robust engineering. If it all works out, if the baby universes do get created, and universes actually can be more common and easier to make than a single brain, because universes are small when they start, and brains are big and macroscopic, it doesn't matter what your initial condition is. This will naturally happen in a very generic way, which is a nice feature. It just relies on a huge amount of very sketchy physics that we don't understand. So the new thing is taking seriously the finite dimensional case. So up until this year, I would have told you the finite dimensional case can't possibly work. What happens is, you get this evolution on the torus of phases, you plot the Boltzmann entropy, and like Sakshi told you, we started very low just because we say so, not because of any principle, and then it goes up to equilibrium and it fluctuates around. And remember, the recurrence time is very, very long, so I just can't plot it long enough, but if you plot it long enough, you would go back downward in accordance with the recurrence theorem. But the huge problem with this is is absolutely dominated by Boltzmann brains. If you put in some phenomenologically reasonable numbers, the time between the fluctuation into a brain is about 10 to the 10 to the 66 years, which is a lot. But it's very, very, very small compared to 10 to the 10 to the 122 years. So the overwhelming majority of observers in this cosmology will be Boltzmann brains, and I would have told you, therefore it doesn't work. The loophole is, what about that commensurable case? What about the case where the eigenvalues are all integers times some number? Then you don't fill the torus. You come back and repeat exactly on a much shorter time scale. So now I can show you a plot that actually has these not recurrences, but periods, exact repetitions. These lines up and down, this is entropy versus time. The line at 0, 1, 2, etc. These are real lines. Those are not just on the graph. Those are the entropy going down and coming back up. So to expand it a little bit around one of them, the entropy is fluctuating around, it goes down and comes back up. This happens much, much quicker than the recurrence time. If you fiddle with the numbers, and again, there's no claim that this is in any sense generic or natural, but you can do it. You can fiddle with the numbers in such a way that the overwhelming majority of observers in this cosmology are ordinary thermodynamically sensible observers, not randomly fluctuated Boltzmann brains. Just because you repeat the universe much more often than expected. So what would this look like from a space-time point of view? We can only wave our hands. We do not have the map from Hilbert space to space-time in nearly the reliability we would like, but I think just from knowing what it does, you can more or less say what space-time has to look like. You have a long time in equilibrium, which is de Sitter space, and then suddenly, like, occasional photons begin appearing out of the thermal bath around you, and there's more and more of them, and it is exactly our expanding universe that goes from a Big Bang and cools, but run backward in time. So you go from equilibrium, you collapse into a big crunch, you bounce, and then you Big Bang. And there is, once again, absolute symmetry with respect to time, because there's an arrow of time from the bounce going forward that way and also backward that way. So the bounce, by construction here, is a minimum of entropy. Why is it that way? Only because I said so, not because of any principle, but it's allowed, okay? It's a loophole, and we're exploiting it. And this happens infinite times. It happens again and again. In fact, it's exactly periodic, so if you want to, you can just think about it as a circle rather than as a line, the evolution of time. You can wave your hands about the metric and things like that. It's a little bit weird if you're a working cosmologist, like how can the universe recollapse if I don't get rid of the cosmological constant, but we have a story to tell about that. The really amazing thing is it really is exactly periodic. There's many examples of cyclic cosmologies on the market, where the universe expands, contracts, bounces, expands. Essentially none of them are truly periodic. Either the scale factor or the entropy or something grows monotonically with time through all of the cycles. This is not like that. This is really saying that what is happening in this room right now has happened an infinite number of times in the past in the wave function of the universe, and will happen an infinite number of times again. Those philosophers in the audience will think this is a familiar kind of story. So just to do one little thing to assuage your worries a little bit, you may have been told that in Everettian quantum mechanics, branches of the universe can decohere and split, but they can never rejoin. That's because you weren't talking cosmologically. Like, in the next few years, they will never rejoin, but cosmologically, they absolutely will, and it's kind of an interesting thing. We say that branching is irreversible because of decoherence. What you mean is, I have a superposition in the system, state 1, state 2 environment, and they become entangled, and the environment states are orthogonal, so that's decoherence. If you wait long enough cosmologically, it's not that the environment states line up again in some rare quantum fluctuation. It's that the system states line up again because everything looks like empty de Sitter space. So if 1 and 2 evolve into the same quantum state, then it doesn't matter what the environment's doing. You can just write it as E3, and it is once again a product state. There's no more entanglement there. So the entire branching structure of the universe repeats every cycle, not just one branch. I will end with some deep thoughts, not from myself, but from my illustrious forebears. It was Poincaré who came up with the Poincaré recurrence theorem, and it was late 1800s, and he knew exactly about statistical mechanics, and he was French. So he knew that like the big believers of statistical mechanics were English, and he liked to make fun of them. So he said, according to my theory, to see heat pass from a cold body to a warm one will not be necessary to have the acute vision, intelligence, and dexterity of Maxwell's demon. It will suffice to have a little patience. And we are, in a very real sense, making that musing come true. Or in slightly more dramatic form, the eternal hourglass of existence is turned over again and again, and you with it, speck of dust. Thank you.
Now it's time for the comments from Niels.
Yeah, thank you very much. Thank you very much, Sean. So I think Sean and his co-host has a very intriguing account of the arrow of time. And for instance, if I can speak for the emergent elaboration, we've also been a big fan of the Hilbert space fundamentalism, about the question how to get space-time out of that. Yeah, so in that sense it's very much interesting. So what I'm going to do now, I'm going to mainly focus on your paper with Sakshi and Nadia.
Nadia.
Yeah.
Two eyes, yeah.
Yeah, exactly. Because that's what I look at best. And let me start with half a question, half a comment. And this relates to how to evade Boltzmann brain domination, right? So picture that of a cyclic, cyclic cosmology with a kind of period time, let's say T star, right? And to get this Boltzmann brain, to avoid Boltzmann brain domination, you want this to be smaller than some big number, right? Can you read it or?
No.
Okay, I mean, I mean, it's a big number, it's a more doesn't have, okay, one second, let me just
Much better.
yeah, okay. And what I don't really get is how you get to this number effectively, so to speak. I mean, the thing is, you do some general considerations of what t star could be, with a lower bound, upper bound, and the first naive estimate gets you a t star of, yeah, somehow e power to 10, power to 1, 22, so which is many, many magnitudes larger, right? And then there's certain arguments involved, I think, about symmetries, degeneracies, etc. And it would be much appreciated if you could somehow spell it out, because I think, I mean, just for illustration, this is like 10 power to 121 magnitudes, so the order of magnitudes different, right? So, I mean, not 121 orders of magnitudes, but about 10 power to 121. So you kind of wonder, isn't it really, I mean, you said non-generic at some point, but isn't it really very particular? And why this seems to matter is because as long as there's no good explanation for why you really get into this regime, all we seem to be able to do is to say, well, pose it that there are no Boltzmann brains, then I can basically derive such a constraint, and I can basically, all of this ensemble of models, I can just look at certain kind of subset of models which I take to be somehow self-consistent, not undermining. But in that spirit, you could even take a model which is a much longer period time, which has Boltzmann brains, and just restrict also to a space-time region, I would say. So you could also simply say, require that there are no Boltzmann brains, so to what space-time regions, basically in the spirit of the weak entropic principle, do I have to limit myself? Okay, that would be the first remark in question. And the second one is really one about the overall project. So you call this model phenomenological, right? You also create this link to Nietzsche, so you're kind of attempting a re-evaluation of values besides those of quantum mechanics, right? But to what extent do you really want to do everything from scratch now? Because obviously you use certain ideas, like the Janus point, cyclic universes, etc. Do you still somehow plan to connect to certain approaches, say, canonical quantum gravity, Z cosmology, loop quantum gravity, or do you think this really points to new, more fruitful direction, I think, as you also hinted at in your talk, yeah? I think this would be, for me, I mean, I would have one more question in a way about the Hilbert space fundamentalism in general. What about time there? I mean, is this also something you think about? What role to give to the, let's say, kind of more quantum nature of time, if at all? Yeah. These are my
Okay, good.
points, yeah.
So yeah, about the Boltzmann brains, like obviously this is another thing that one could give a whole talk about, and shockingly, when I give talks that mention Boltzmann brains, people do not just agree with everything that I say. They have opinions, which is good. And I think that what Niels points out is something that I did kind of allude to, but he's worried about it, and all I can say is you're absolutely right to be worried about it. So remember that what we did was we imagined that there is a finite dimensional Hilbert space with a spectrum, and the energy eigenvalues are integer spaced, or they're commensurable to each other. Okay, so they're all integers times some tiny value of the energy. What is that value of the energy, right? And that's just a free parameter in the theory. So what we point out is that you might guess this value, we sort of guessed the smallest reasonable value and the biggest reasonable value. And we found that, for the smallest possible value, the period of the universe is like not too much different than the age of the universe now. it's gonna recollapse any minute, and so that's a limit. The other value of the period is 10 to the 122 years. It's a hilariously long time. It's much longer than the time it takes to make Boltzmann brains. So if the value of that in free parameter in the theory is near the upper range of what is allowed, then we do not solve the Boltzmann brain problem at all. There's a little bit of care you have to do to imagine that the number is smaller, because in order to fit all the dimensions of Hilbert space in there, some of them need to have energy eigenvalues that are degenerate, that are exactly the same. And so we point out, like, that's not surprising. You know, anytime you have translational invariance or rotational invariance, you're going to get degenerate energy eigenvalues. Niels's point, which we also said in the paper very honestly, is that you have to be really degenerate. But, okay, that's absolutely true. We are making absolutely no claims to robustness or genericity or anything like that. All we're saying is that this is a loophole in the argument that Boltzmann brains have to rule out finite dimensional Hilbert space cosmologies. There are actually other ways out of it that are even do more violence to the standard structure of quantum mechanics that I don't want to get into, but I think it's interesting you don't have to do violence to the standard structure of quantum mechanics. The question about restricting to a small region of space-time, I don't really think is applicable in the sense that the whole universe, in a very real sense, in this picture is one observable patch, right? It's one observable patch that will be described differently by different observers, but it's a finite size of space. So you don't get like more and more Boltzmann brains because you go to bigger and bigger sizes or anything like that. It's a very clear calculation as to how many there should be per space-time volume. And again, the answer is you can avoid them, but it doesn't just fall into your lap that they are avoided. That's entirely true. The next question was, how do we connect to things like canonical quantum gravity or loop quantum gravity? Well, we don't. We are trying not to. We are not saying that one can't someday, or for that matter, string theory. You could say it's string theory. But we think that the general idea that the universe should be thought of as a Hamiltonian acting in Hilbert space is common to all of those theories. It doesn't matter. So the whole point of an exercise like this is to say that if your fundamental dynamics are something like the Schrödinger equation in Hilbert space, it doesn't matter where you get the Hamiltonian from. It doesn't matter what your fundamental degrees of freedom are. There are certain robust features of what the quantum state can possibly do. And maybe someday we'll find out that, in fact, oh yeah, the right way to get this spectrum of the Hamiltonian is to start with canonical quantum gravity or string theory or something like that, 100% compatible with everything we're doing. The final question was about the emergence of time, which is a super good question. And I didn't get a chance to talk about it just because I ran out of time, whether it exists or not. But remember, well, let me put it back here. The whole starting point, right on the first slide, is that the Hamiltonian is specified by its spectrum, and that's the only data that you get from which to emerge the world, the spectrum of the Hamiltonian. If you thought that the fundamental equation of reality was not the Schrödinger equation, but rather something like the Wheeler-DeWitt equation, where h psi equals 0, okay? Then you don't have any data. Then the spectrum is the single number 0. That's not helpful to say, oh yes, 0 emerges into the standard model of particle physics or something like that. It just can't be done. Well, on the other hand, we think that time exists in some sense. So you have to talk about the emergence of time. And in that case, if you thought that time was emergent, you could absolutely play this game, but there would be an emergent Hamiltonian giving rise to emergent time evolution, and you could play this game with that Hamiltonian, with the emergent one. I do think, and again, it's a separate talk, I think that there's been a lot of work done on the emergence of time. Much of it cheats, because you know what answer you want to get, and you convince yourself you can get it. There's a great worry that's been advertised by Andy Albrecht and his collaborators called the clock ambiguity, that says if you can get time to emerge in one way, you can get it to emerge in an arbitrary number of ways, and you're not really getting anything, which is compatible with the idea that the number 0 is not a lot of data to work with. So I think that the most promising way forward is something like the thermal time hypothesis of Kohn and Ravelli, where you start with a density matrix rather than a pure state. Because then even if the Hamiltonian doesn't have energy eigenvalues, the density matrix has eigenvalues, then you can define the modular Hamiltonian by taking the logarithm of that, and then you can play the game with those energy eigenvalues. So all of these are papers yet to be written, and just make sure you cite me when you write them. Thank you.
Thanks for a very nice talk. I have two different questions, but maybe we can start with two. So I didn't read the paper, but I was trying to skim over and see if you guys talk anything about the Pauli obstruction to define a clock. Not sure if you're familiar with that, but the idea that what if you want to define a time observable in a Hilbert space? In fact, with canonical notation relationship PH equals I. Turns out that by Stone-Malone theorem, that has to have the same spectrum of variables with X and P, but then Hamiltonian is bounded, so it doesn't work. And one way to go around the obstruction is to make the spectrum commensurate. And so people define a clock observable in Hilbert space exactly by the same move that you guys did here. And so I wonder if there is maybe some underlying connection here that maybe there's room to be exploited. The way that not only you find this kind of like arrow time and everything, but at the same time you're defining actually a clock observable in a way that avoids Pauli obstruction. So maybe that's a comment or suggestion.
Yeah, so let me just say very quickly, we simply did not think about time as an observable that you could measure, or building clocks or anything like that. We took time to literally be the parameter that appears in the Schrödinger equation, just for purposes of this particular paper. But I'm absolutely fond of thinking about measuring time using quantum clocks, and if that could somehow lead to a motivation for a commensurable energy spectrum, that'd be really cool.
And the second thing is I'm not sure to which extent you guys want to be provocative and then say things such as what happened in this room is going to happen over and over and over again. Or even this idea that when we are in the equilibrium phase, you do have a space-time. But I was thinking that given what you guys presented here, one could have been much more agnostic about not even having a geometrical phase when you are out of those particular states or this corner of the Hilbert space. And similarly about this idea of being here in the same room over and over again, goes back to the assumption that you factorize the Hilbert space the same way. But you could have thought that actually at each run you are taking the quantum state to the global state and break it down in different ways in Hilbert space, and therefore there is a cyclicity at the global Hilbert space level, but for the subsystems that's not the case anymore.
Yeah, I think the opposite answers to those two questions. For the... Darn it, what was the first question?
About the fact that you have this always a geometrical phase, right? You could actually...
Oh yes, right, exactly, right. Yeah, so honestly, in the draft version of the paper from 2 weeks ago, we didn't have these metrics, and we didn't say that this phase was de Sitter. We just said it was quantum equilibrium. And I think that we sort of hand-wave in that part of the paper. We say, like, look, if you think that the equilibrium state is de Sitter space, then it's going to look like de Sitter space. If you want to just say that it's a quantum equilibrium state, that's also perfectly okay. Like, I am on board with taking seriously the possibility that defining a classical-looking space-time only makes sense in the context of a pronounced arrow of time where you have, pointer states and decoherence and all those things. So I'm completely open to that. But I do think that the cycles are exact repeats of each other in the sense that the ontologically fundamental pieces of the story are just a vector in Hilbert space evolving according to the Schrödinger equation. And that vector evolves in an exactly periodic way. So there is no principled way to say there is a different factorization or macro state decomposition in one phase versus another. They're going to be, whatever applies to one cycle applies in exactly the same way to all the other cycles.
Okay, thank you. Shall we limit ourselves to one question only? Okay.
Many thanks. I really learned a lot. I've been working a bit on the metaphysics of successive universes, more eyes on Roger Penrose's conformal cosmology, but I think some ideas may apply here. I would like to hear if you think that are very speculative or say we're in a situation where there's kind of Hilbert space fundamentalism, and it's finite and the recurrence theorem applies. If you were to add to that, so we had some repetitions like that. If you were to add to that a metaphysical principle, Leibniz's principle of the identity of the indecinables, the fact that suddenly you have an exactly identical state, a qualitatively identical state, by this principle will imply that it's also numerically identical. And then you switch to a kind of a periodic scenario, to what I call the grand loop. So it's kind of closed on itself all the time, like directions of that black holes, basically. And I think, don't you think that? So maybe it's very speculative. So maybe something is wrong there. But if that works, could it help to address the threat of Boltzmann's brains by because if the probability of getting to one of the states is a lot bigger than the one of Boltzmann's brain, then it will have killed the threat, right?
Not quite.
Okay.
So I should get on the table that I'm not a fan of metaphysical principles as a general rule. We do say in the paper that you absolutely could mod out by the period and treat time evolution as happening on a circle rather than on a line. And what we literally say is, it's a matter of taste. Do it the way you want to do it. I don't think there's any strong argument that it has to be done one way or the other. But I also think very strongly it has no bearing on the question of whether or not you're dominated by Boltzmann brains. That question is just a matter of how long this period is, not how many of them. So you're right, for all intents and purposes, I can take the time evolution of the universe to be finite between there and there. But what matters is the total entropy of this period and how long it lasts. And if it lasts longer than 10 to the 10 to the 10 to 66 years, then there will be more Boltzmann brains than ordinary observers.
Yeah, so on Boltzmann brains, I suppose that you're familiar with the papers by Rovelli and Wolpert on why you shouldn't worry about them. So I'm still not sure if I'm in line with them, but to the extent that I understand them, they seem to assume that it's not really problematically rational to believe that you're a Boltzmann brain in any sort of situation, because either you can actually rely on the data they use to assume that the laws of nature are symmetrical and this and that. In that case, you're actually not allowed to believe the situation that you think you were in. If you're allowed to believe that rationally, then you have some proof to the extent that the data that they have is reliable. But the data can only be reliable if you have reliable traces in the environment, and for that you actually need the entropy to rise, and that's hypothesis and this and that. So do you agree with that sort of purely in terms of rationality they shouldn't worry about? Are you, in your view, are you only just thinking about the physical emergence of Boltzmann brains and trying to see if you can actually avoid that situation? Or are you also thinking that a good theory shall worry about that because Boltzmann brains are intrinsically problematic?
Yeah, I think they're clearly wrong, and you should worry about them, and the way to get rid of your worry is to invent cosmologies where they do not dominate the number of appearances of observers like us. The way that they're wrong is you're allowed to, it's very similar, the move they make is very similar to an older move by Jim Hartle and Mark Strednicki, where they said, look, I look around and I know I'm not a Boltzmann brain. Doesn't look like I'm a brain floating in empty space. If I live in a universe where most observers are Boltzmann brains, I can just say, but I'm not one of them, so there. And then I can just go through my day, happily. The problem with this is that most people, in their exact macroscopic state, would be random Boltzmann fluctuations. And therefore, given this physical setup, in their way of thinking, you should still predict that when you go outside, it should be thermal equilibrium. You can't have the God's eye view that lets you say, not only here is the set of all possible observers, but there is self-locating uncertainty between observers that are in exactly the same epistemic state, and I know which one I am. You don't know that. You're inventing a theory where most observers are going to be wrong about what happens next in the world, and you shouldn't do that. That's bad science.
There was one hand, otherwise there should be Volta and then Volta Did you raise your hand?
Yeah, okay, just have a question.
Yeah.
Okay, it's an embarrassingly basic question. I'm sorry for that, but just for my comprehension. So, the theory here is not that at any proper part of this diagram there's like a double arrow, but rather that at different proper parts there are arrows in different directions, and that at the de Sitter equilibrium there's no arrow whatsoever. So, right or not?
Right.
Okay, so that's so that's kind of the question. It was embarrassingly basic, but I was just trying to understand, like, what do you mean with like double?
The arrows are where I drew them.
Yeah, okay, nowhere else. No, okay. So in what sense then is it cyclical? Like, I mean, like at the point where time has a direction, it's not cyclical. So like
There can be time without an arrow.
yeah, sure.
So there is time, and it lasts 10 to the 10 to the 10 years or whatever, and then the universe repeats.
Okay.
For most of that time, you're in equilibrium and there's no arrow.
Okay.
That was it.
Was it confused? I think you raised your hand as well, right? If you don't mind, you go and then it's yours. It's okay.
I'll give you short answers, don't worry. Bad.
Yeah, we'll have half an hour still. Okay.
So, my turn, okay. So I have a question about your picture where we were decreasing and increasing. And I just, okay, so if you reverse the arrow of time, and that brings with it a reversal of the arrow of causation, then it seems to me there's this interesting possibility, which is that even though objectively, in some sense, the arrow is reversing, the experience that the individual is embedded in that space would be just the same as if the arrow was going the other way. And so we actually get twice as much experiential occurrence. Yes. So I just wanted to,
Almost. You're almost there.
okay, all right, so
You're 100%
yeah.
right
Okay.
that I'm a fundamentalist about the arrows of time also. So I think the arrow of causation and memory and all those things are all supervening on the thermodynamic arrow.
Right.
So there is, everyone always defines the past to be the direction of lower entropy. So I put you are here just to
Yeah.
stop people like you from asking those questions, but there's another one over here who says this is the past and this is the future. But if you look super carefully, the wiggles on one side are not exactly the same as the wiggles on the other side.
Okay.
You can see it over here.
Yeah,
They look very similar, but if you go
I
far
see.
enough, they're not exactly the same.
Okay, so you can get out of that. But I think it would be an interesting consequence if that
It,
was the case.
you can make it happen by
Yeah.
cleverly choosing the initial state.
Yes, okay.
And then you're right, you get one more duplication.
Okay. Yeah.
Go ahead.
I have a question between the connection of the cyclic universe and statistical reasoning. So when Sakshi was presenting her conception of entropy, was sort of saying that entropy increases over time because the vast majority of Hilbert space is a high entropy sector. So if we choose one state to be the lowest one, then as the evolves, it's very probable that it goes to the high entropy sector. But in this specific case, where we're looking at a very, very specific trajectory, where we actually don't have access to the vast majority of the space, right? It's a closed loop, it's a small thing. Are we guaranteed that this very, very specific loop follows this kind of statistical thing where it's very likely that it goes to high entropy and back again? specific evolution, are we guaranteed that we get some statistical mechanics as evolution as we're used to it? And even if it's a very, very initial low entropy, there isn't any, like, so we're guaranteed we will for sure increase somewhat. Are we sure it looks anything like our world, for instance?
So those are two slightly different questions. Your first set of questions involved the words guarantee. And no, there are no guarantees in life. So if you have a box of gas with Avogadro's number of particles in them, and you think that you're going to do standard statistical mechanics, but someone has lined up the initial conditions so that all the gas molecules move exactly horizontally, you're not going to get any increase in entropy. You could absolutely imagine a similar thing here where there was a weird matchup between the specific evolution of the state and your choice of macro states so that the entropy never went up. That's absolutely possible. But if you don't do that, if you have more or less generic looking macro states and things like that, this is something more like what we will get. And I think that the arguments that Sakshi tried to give are pointing in the direction that with this definition of quantum Boltzmann entropy, it has the properties that on each branch, there is some classical looking space-time that you're in and so forth, and you are described by a pointer state that lives in one particular macro state. You get ordinary statistical mechanics just as much as you thought you ever did from Boltzmann's tombstone, S equals K below W. So you don't, if you have an issue, it's not with us, it's with Boltzmann.
Okay, there is a question and then it's Neil.
Yeah. So, thanks for the talk. I have a question about the kind of like very strong conclusion that the exact periodicity is enough to kind of like have this the Nietzsche version of like equation in the sense of like up to kind of like the single individual action and so on and so forth. In the sense of like I don't see how, I mean like if you're like talking about like on a cosmological level, it seems like you can have exact periodicity without kind of like that implying I'm gonna say the exactness of repeating the same action appears on a kind of like human scale, no? I mean, it seems like you could have periodicity on kind of like cosmological scales, or like kind of like a more coarse-grained version. Seems like the parameters you're considering as cosmological parameters, but that's kind of like not. It's not enough to determine that these happen on kind of like on all the degrees of freedom. No?
I think it does. So the idea of the setup where you have a single quantum state describing the universe is not that we're doing some kind of mini superspace quantum cosmology. We're doing the theory of everything. We're imagining that all of physical reality is described by a finite dimensional Hilbert space, and that includes you and the cat and the stars and everything else. And there is a branching structure. In fact, it's a really kind of interesting story to be told. Remember, I alluded to the complexity story. But the universe at the low entropy part is very simple, and there's not a lot of differentiation into branches. When inflation reheats and you get all these particles and everything, then you branch into a million different things, and the pattern that we see in the microwave background is one particular realization of a random field. But all the other realizations are there in other branches of the wave function. So all the complexity of our phenomenological universe is self-locating uncertainty because of what branch we end up in. But the entire set of branches will repeat exactly over and over again.
But that's not, I mean, that's not what cosmology thinks they're doing. Like, cosmology don't think they're doing the theory of everything when they do cosmology. Right? So it's kind of
some of us do.
Okay, yeah, fair enough. But like the calculation that you were showing up, they're like, in the cosmological side. I mean, you can actually compute that.
The idea, which I tried to stress, is very far from being completely fleshed out in real life. The idea is that the theory of everything has a Hilbert space of dimension 10 to the 10 to the 122, that there is a way of mapping specific states in that Hilbert space to superpositions of classical-looking spacetimes with people and fields and photons and all that stuff in it. I don't know what that mapping is, except for some hand-wavy ideas, but that's the aspiration.
Yeah, so normally skeptical challenges come in all kind of forms, and we can maybe sort them, so to speak. And the especially interesting thing about the Boltzmann brain is that somehow the skeptical challenge naturalized somehow in our physics.
Yeah.
But I'm just wondering whether not even with this you can somehow say, just like you walk over other skeptical challenges, now even if it's nicely put in terms of graphs and physical equations, whether you should after all also step over it and just continue working. I mean, I think you have definitely reached some cognitive stability about that this is a problem for you, but you still sometimes feel fluctuating, in this direction, or is it...
So I do not, and I think that, because the beginning part of your question, I think answers the final part of your question.
Yeah.
It's not only that there's a physical mechanism that gives rise to the skeptical scenario, is that there's a measure. So you can ask conditional probability questions in this kind of scenario. You can say, given that I observe X, what is the probability I will observe Y? Right? That's what you can't do in bringing it back kind of scenario. And this makes, just like we were saying over here, very strong predictions for what you should observe next, and nobody believes those predictions. And I think that the reconciliation is invent a theory where those predictions are not true. There is, I'm burying a little bit of a super worthwhile discussion about the anthropic principle and self-locating uncertainty and things like that, right? And I would say that, you might have your opinions about the anthropic principle, but if you have a cosmology where there are multiple observers who are in truly indistinguishable epistemic states, you should give whatever counts as equal probability to being any of them. You don't get to pick which one you are. That's helping yourself information you don't have access to. You're not allowed to ask a question. We have time.
So I want to know what happened in the 2 weeks between saying quantum equilibrium did not have emergent space-time and actually it might have emergent space-time. And maybe just this group of people would be interested in why we were going back and forth, and really the issue is recoherence. Thus far we were tying emergent classicality to decoherence, but once you are able to factor out the de Sitter space component on each branch and you have recoherence, in what sense then do we still want to consider the equilibrium phase as having the emergent de Sitter space?
So I think that is an important consideration, but it was not really the stumbling block to writing down the metric or the space-time. The stumbling block, for those of you who do cosmology in your spare time, is that there have been plenty of people working on cyclic cosmologies in one way or the other. And you need two pieces of magic to happen in a cyclic cosmology. One, you need to have a bounce, right? The universe needs to collapse in a big crunch, and then not just hit a singularity, it needs to bounce and have a big bang. But the other is you need to recollapsing things, right? Like you're expanding and you're going to dilute everything away, and then the universe has to recollapse. And there is lore that says the universe is never going to recollapse if there's nothing in the universe but the cosmological constant, right? You have a way of slicing the universe, it expands, the scale factor goes as e to the ht, and h is a constant. So the universe is just expanding forever and ever and ever. So you can't recollapse unless you have some dynamical dark energy or some other funny business somehow. And I knew that that didn't really apply to our case, but it wasn't clear exactly how to say the words about how to get a recollapse without changing the energy density of the universe. And the answer is how you slice the universe. So de Sitter space, which is the conformal diagram of, is maximally symmetric. If I just pick any point in de Sitter space, there is no answer to the question, is that point, at that point, with respect to time going vertically, is the universe expanding or contracting? That's not a well-posed question. Expanding or contracting is a feature of slices, of foliations, not of points in de Sitter. So as you approach de Sitter in the future, of this cosmology, you approach a maximally symmetric situation where there's no such thing as, you can't say the universe is expanding or contracting. The way to reconcile the fact that it was expanding and emptied out with the fact that now it's going to start contracting is that it's not in the same foliation that those two statements are true. You have to re-slice the universe in a different way. So that's where we get, well, I don't know. I could probably try to say it here. The simplest way to do it is the expansion part of the universe can be described by just slicing horizontally. Then you get a three-sphere positively curved geometry. The sphere can be really, really big so it can look flat. And then you get exponential expansion toward the future. But you can also slice it in what's called the static patch slicing. So in this triangle, which is the causal diamond of one observer here at the North Pole, if you slice by starting at the point, the bifurcation sphere right in the middle, and slice by going to the edge, those slices are static. They're not expanding or contracting. They're also not homogeneous, so they're not FRW. But the trick to building a metric that works everywhere is to say that when there is matter in the universe, there's a natural slicing, which is just the horizontal FRW slicing. When there no longer is matter, there's a more natural slicing, which is the static patch slicing. And then it goes back into a collapsing FRW slicing. So putting that story together was just a stumbling block in L rings. And then, of course, once you get it, you can start making statements about, well, is it really recoherence and things like that.
So recoherence does not undermine the emergence of space-time?
No, I don't think so. I mean, again, like we were saying, should we even assign geometry to that part of the story? I think it's something that I'm not super confident about. So I'm confident that you're allowed to. I see no obstacle to doing it. I'm not confident that you should. And I'm not sure it's the right thing to do. If you didn't want to, so the words we had in our draft of the paper were, look, you might be tempted to say this is de Sitter space, but what does that mean? At least have some operational meaning with respect to like test particles or observers or something like that. But there literally aren't any such things. There aren't any particles in this part of the universe. It's just equilibrium. So in a very real sense, there's no reason to call it de Sitter space. Again, I'm not quite sure that it matters, but okay, that's where I am.
Okay, I think we have run out of time at this point. Yeah, so let's thank Sian again.
Thank you.